everyone, welcome to fifth video of our series Introduction to Statistical Testing with R. Today we are gonna be talking about correlation and regression, and then in the next video I'll be continuing with some other regression methods. So without further ado, let's start. We are gonna be starting with correlation. So let me talk about what correlation is and correlation analysis specifically. So correlation analysis helps us assess the strength and direction of a relationship between two variables. In statistics, correlation values range between -1 and 1, 1 being a perfect positive correlation where an increase in one variable is directly proportional to an increase in the other one, and -1 being a perfect negative correlation where an increase in one variable is directly proportional to a decrease in other. So if the correlation value is 0, it means that there is no correlation, meaning there is no discernible relationship between the two variables. This was the obvious part, so now let's go more in depth. There are three types of correlation measures based on the characteristics of data. We have the Pearson correlation, then we have the, Spearman rank correlation, and then lastly we have the Kendall's tau correlation. So let's start from the Pearson correlation. So this is the one we mostly use because it measures the linear relationship between two continuous variables, especially in statistics. When I was taking it, I was looking at this mostly because when we think of correlation, the correlation we understand is usually the Pearson correlation, because if we are not really going into depth in statistics, we don't usually look into categorical variables and the correlation between them. So here this is for data when it's normally distributed and linearly related, and the formula is this. Let me show it to you. Here you can see the formula. We have the correlation symbol, and then we basically take the x component and the y component, subtract the x and y means from those and then multiply them and take the sum, and then divide it by by both different summed up and both different squared and then summed up and their square. That's the Pearson correlation. And then we can now test it because I've already talked about how to interpret it, which one means perfectly positive correlate and -1 negative correlated. So wait, oh, it's here. So we are gonna be creating our data. Oh, I wasn't writing. It's so funny of me to do this. Variable 1, which is, let's say 10, 15, 25, 30, 45. Variable 2, 12, 18, 28, 35, and 40. And Pearson say correlation. We just say correlation.test. We take the variable 1, then we take the variable 2, and then as method we give Pearson. Now we can actually look at the result. Let's run this. Oops, it was, yeah, now it works. Okay, so what do we see here? First we see the t statistic, which is equal to 6.584. This indicates how many standard deviations the observed correlation coefficient, which is here 0.967, is from 0, which is the null hypothesis, because null hypothesis says they aren't correlate at all. There is no discernible relationship between them, linear relationship, which so the t statistic is the standard deviation difference. How many standard deviations is this observed correlation away from the null hypothesis 0? Okay, a higher absolute t value would obviously suggest a stronger evidence against the null hypothesis, which in this case says that there is no correlation, again to remind you. Second, we have the degrees of freedom, but we have to be careful here because it's kind of tricky. Since the first article, I've been saying that degrees of freedom is n-1, so number of samples -1 or number of groups -1, but in here it's n-2. So you can remember this since correlation has two R's, and R is the symbol of correlation, and inside the word correlation there are two R's. Maybe this is just a method that I've thought of to remember it myself. And so since the number of observations here is 5 in each variable, it's 5 minus 2, 3. And then the p-value is 0.0071, which is less than the 0.05, the significance level we've been taking since these series. And then this suggests that the observed correlation is statistically significant, and we can reject the null hypothesis and say that the variable 1 and variable 2 are correlated. And then we also have 95% confidence interval here, which is from 0.578 to 0.998 approximately. And this interval tells us that with 95% confidence, the true correlation coefficient lies between these two values, which indicating a strong positive association, because 0.5 is like kind of medium, like moderately correlated. 0.99 is more near 1. So it means a strong correlation. So since it's above 50%, we can say that it's moderately correlated or strongly correlated. So this means that they are highly correlated. If they were between 0 and maybe 0.1 and 0.4, we would say they are slightly correlated but still correlated. But we can definitely say here that there is a strong positive association. And since they are positive, there is a positive association, we can confidently say that. Anyways, now, and then the sample correlation coefficient is 0.967, and this again suggests a positive linear relationship. So as the variable 1 increases, variable 2 also increases. Now let me show you how to plot this, because plotting is always my favorite part. Why can't I click on this? Oh, now I can. Great. So again we have ggplot. If you come back to this video, it might have been lost. You might have opened R the first time. So by now I think you have memorized this already. We have x, variable 1, y, 2, and then we'll do a scatter plot here. Point, let's give blue. Is it too dark though? Let's see, maybe royal blue. I love these kind of pastel colors. Size 3 for the scatter plot points. If you want to make them bigger, you can play with this. Jump smooth. Now we want to create like a, how to say it in English, a linear regression line with confidence interval. So geom smooth will basically give us that, and you will see the confidence interval. It looks really good. Okay, same method, linear regression library, color orange, yeah. And then fill, let's make it, do we have green? Yes, that's better. And then alpha 0.2, shouldn't be really transparent. Okay, then labels, title, Pearson Correlation, visualization, subtitle, red line, linear regression, fit with 95% confidence interval. I think it's a good subtitle. We want to be as specific as possible if we want to present it to another person, especially if that person has no idea about these but wants to use these kind of insights. That's what data scientists do, which is really cool. Also, then T minimum. Okay, now let's see. What did I do wrong here? Object labs. Oh, there might be a problem here. I see. Oh, now it works great. Now you can see it looks good. Okay, this is just an information. So here we say, but it's not red line, it's orange line. Okay, let's do it again. So here you can see the confidence interval. So how much the model thinks that we might deviate according to the correlation. So it might have this value which would indicate like a better correlation, or this value like less steeper. So it can change between that, like the line can move between these values. And then we have our points, and then we have our regression line, and we can see the correlation. If they weren't correlated, then this wouldn't be steep. If I had given this, for example, 1, 2, 3, 4, 5, they wouldn't be correlated. See, are they correlated? They are. That's funny. Yes, they are, of course. I should have done it like 1, 10, 3, 7, 0, 1, 2 maybe. Okay, let's see. This one, now they won't be correlated for sure. Yes, they do not, because it's like going up down up down. It's not like consistently increasing or decreasing. Yes, now you can see it. It's like not steep at all. It's like in the middle, no correlation. But we want correlation, so let me change the values to their first positions. Great. Now what do we have about this? Nothing more to say actually. So let's move on to Spearman's rank correlation. So this is a non-parametric measure that assesses the monotonic relationship between two variables. It's useful when data does not follow a normal distribution or when dealing with ordinal data. So as I mentioned here, it's for non-parametric, so it's for not normal distributed data, and also for ordinal data, so categorical data. You can use it when your data doesn't meet the assumptions of normality, or when the relationship isn't linear but still monotonic, which means it's consistently increasing or decreasing, but it isn't necessarily a linear relationship, and you see what I mean. So we calculate this with a more complex formula. Let me take it to the screen. The P is the Spearman's rank correlation coefficient, the I is the difference between the ranks of corresponding values of x and y, and is the number of observations here. So we calculate with this, and then one last thing to again emphasize, Spearman correlation ranks the values before calculating the correlation, so it's suitable for ordinal or ranked data. That's why it's suitable for them. Now let's implement this again. I will have we can stay with the same data. Okay, let's see. 820. I've changed a little bit here, but it doesn't make much difference. Can just take it here, then Spearman correlation. We again say core.test, so the same, which is really efficient to use. You just change the method. Varman data variable 2, and this time our method is Spearman. Now we can see it. So first of all, we have the Spearman correlation coefficient denoted as P, shown in the result as RHO. It's important to know that because P is rho symbol from Greek alphabet. So if you don't see P here, you can directly know that rho is P. So it's 1 in this case, which indicates a perfect positive monotonic relationship between variable 1 and variable 2. But like, I mean, this is obvious because it ranks the data, so it just looks at if the data points are increasing for both of them consistently or not. So if we had made this like kind of jumpy, increasing, decreasing, increasing, decreasing, now you'll see that the rho is even minus, which is like really I think that you won't see much, which means no relationship. Correlation. So again, this means that as variable 1 increases, variable 2 also consistently increases in a ranked order. Also, let me show you this. 35 too. Okay. Now if we run this, we get -1 because we always like look at the correlation results with the same statement. If it's 1, perfect positive correlation. If it's -1, perfect negative. So if 1 is consistently increasing and 1 is constantly decreasing, then it will be a perfect monotonic relationship. And if it's kind of jumpy, we get values like -0.1 or so, really near 0, so no correlation. Okay, now let me reverse this. What did I do? Oh, wait, why did I write it with 2 ends? Okay, now let's continue. So this time we have the S statistic, which is a measure used in the calculation of Spearman's correlation, but it's not often interpreted directly. It's very close here, which reflects the perfect alignment of the ranked data. So a statistic is basically, it's not interpreted directly, but still I want to talk about, so that you have no question marks in your mind. In Spearman's correlation, each data point in one variable is ranked against data points in the other variable. The S statistic measures the sum of squared differences in these ranks and serves as an intermediate step in calculating the Spearman correlation coefficient rho. And lower values of the S statistic indicate a smaller difference in ranks between variables, which corresponds to a stronger monotonic relationship, either positive or negative. And the perfect monotonic relationship, for example, would yield an S statistic very close to 0, which we have in this case. So this is how we calculate the S statistic. We have the Ri here and the Si. So ranks of 2 variables bar Ri and Si. These are the ranks of 2 variables. We take the difference and then square it for each observation and then get the sum of it and find the S statistic basically. And if there is a huge difference between the ranks, we will get a like higher S statistic, and if they are not really different, we would get a lower one normally. This wouldn't really like show the correlation, so that's why it's not directly interpreted. Normally we interpret the rho or the p-value. Here the p-value is less than 0.05, so we observe that the correlation is significant, and we can reject the null hypothesis and say that the alternative hypothesis is true. So the true rho is not equal to 0, which would indicate that there is no correlation at all. And let's also visualize this. Plot data variable 1, y is variable 2, let's point. Again we want a scatter plot. This time let's say pink, and then size 3 again, our line, new regression. What should we do the color? I wanted lime, but we don't have lime here. I think we have dark green. Yes, that's good. And then say SE is false. Then line type is dashed. In this case, we don't need the confidence interval, so we set SE false, which is the standard error. And then what do we have? Oh, we have another one. This is nice, but this time it's different. For method, we are taking the lowest. I don't know if I'm pronouncing it correctly. Let's make the color. Do we have gold? Yes, that's good. And then again SE is false. So this will the first one will give us the linear trend line, and the second one will give us the smooth curve for monotonic trend. So it won't be linear, it will be non-linear, but it will still show a monotonic relationship, as you'll see in some seconds after we give the labels. Title is scatter plot of variable 1 and variable 2. Subtitle is dashed dark green line is the linear fit. It's good to clarify these things. And then the gold line is the monotonic fit. Then for x-axis we have the variable 1. For y-axis we have the variable 2, y2 plus t minimum. And of course we shouldn't forget these things. Wait, where did I? Now it's working. Okay, that's good. Let's see now. So here we can see it. We have the linear fit as dashed green line, and the gold line gives us the monotonic like fit here, and it's not linear, as you can see. It's curvy kind of, but it still shows a monotonic relationship because as variable 1 increases, variable 2 increases too. And so in this case, how do we decide if Pearson or Spearman's we should use? Which one should we use? If the green curve captures the upward or downward trend more accurately than a straight red line, which is true in this case, Spearman's correlation would be preferable as it's better suited for monotonic nonlinear relationships. And do we have another thing to say? Okay, this was all. Now let me give you the last one, just Kendall's tau correlation. This is another non-parametric measure of the relationship between two variables. Let me also put this here. So it assesses the strength and direction of association based on the relative ordering, so the rank of data points, making it particularly useful for ordinal or nonlinear data. So first let's talk about the Kendall's tau, denoted as little t. So it measures the association between two variables based on the concordance or discordance. And they basically mean that concordant pairs are the pairs like if the let's say, so we have the first row, we have 5 and 6 in the first row, and in the second row we have 7 and 8. So both values increased in both variables, right? These are concordant pairs, they both increase or decrease together. Discordant pairs would be if 5 became 4 and 7 became 8, then one of them is decreasing, one of them is increasing. So that would be discordant pairs. And here you can see the formula for calculating Kendall's tau. So concordant pairs minus discordant pairs, and then we have the number of samples here. Okay. It also ranges from -1 to 1, 1 being perfect positive monotonic relationship and -1 being a perfect negative relationship. And the higher absolute value of tau suggests a stronger monotonic relationship between variables, with positive values indicating concordance and negative values indicating discordance. Let's see now. We again have another data frame. Kendall correlation. Test data variable 1, variable 2, method in this case is Kendall. Now let's see. Here we got the Kendall's rank correlation tau. So the tau values here is the t, Oh sorry, this is the one. That's the t statistic which we'll talk about in a minute. But first let's talk about tau value. It's 1, so it indicates a perfect positive correlation because one of them is increasing and the other one is increasing too. So it's a perfect positive monotonic relationship, and this means that so there are no discordant pairs, all of them are concordant pairs, they increase together. And we can actually talk about the test statistic now. So the t equals 10 is a value used in calculating the p-value. It reflects the number of concordant and discordant pairs in the data because it's calculated based on the ranks of the data points and is used to determine the significance of the correlation. However, it's less commonly interpreted directly as the tau itself, and the p-value shows us if there is a significant rank correlation. But still, oops, I hate it when it expands like this. Here you can see how it's calculated. And then the p-value is less than 0.05. So this supports the alternative hypothesis that there is a non-zero correlation between variable 1 and variable 2. And that was all from this. So it's really easy to do correlation analysis, as you can see. The second thing we are going to be talking about is regression. It's also quite simple, but it might be a little bit more confusing because there are a lot of regression types you can use, and we'll learn about the most used ones. First of all, what's regression analysis? So regression analysis is a statistical method used to examine the relationship between one dependent variable, which is often denoted as y, and then this is the outcome or the variable we want to predict, and one or more independent variables which are denoted as x, which are the predictors or variables that influence the dependent variable. And this analysis estimates the strength and form of the relationship between dependent variable and independent variables, and allows predictions and inferences about dependent variable based on the values of the independent variables. Before we start, there are two terms that I want you to know. First of all, but I think you already know these, the coefficients are the values that indicate how much the dependent variable is expected to change with a 1 unit change in the independent variable. These are the values we put in front of the x term representing the independent variable. So the error term, also known as the residuals, is the difference between observed and predicted values. So in this case, observed is the one we get from the data, and predicted is the one when we plug that observed value into the plug the independent variables we had for that observed value into the equation and then get a dependent variable value. That's the predicted one. So first we have the linear regression. Linear regression estimates the relationship between a dependent variable and one or more independent variables by fitting a linear equation to observed data. So in simple linear regression, there is one predictor variable, while in multiple linear regression, there are multiple predictors, and we'll see that. So here is the equation. Y is the dependent variable, B0 is the intercept, also known as the bias sometimes. So B1 is the coefficient for x, and we also have the error term epsilon. So where do we use it? For predicting house price, it's usually used. I'm sure you've seen on the internet many times where we have the bedroom numbers, room size, location of the house, how old it is, etc. And it creates a multiple linear regression. Sales forecasting, again, stock market prediction, these are all examples where simple or multiple linear regression might be used. For that, R gives us a really good data set that we can use, which is MT cars data set, which is a data set about cars, as the name indicates. So we just call the LM and then create our model. We enter the formula. MPG is our dependent variable which we want to predict, and then we have the VT, and we put the data. That's all. One dependent variable, one independent variable, and then summary gives us everything we need. Why can't I write? Okay, now let's run this, and here we get everything. So first of all, we have the call, which shows the formula that's used to fit the model. So MPG is again dependent variable and weight WT is the independent variable. If you see me saying VT, it's normal because I also know German and W is pronounced as V. But don't worry about it. You'll probably think that I'm referring to W. So here we have this formula. How do we get the formula of this from looking at these values? I want to show it here. We take the intercept, which is, look here, intercept estimate 37 point something. Then we get the slope and multiply it by VT. And the slope is the weight estimate here, as you can. So by taking both these values, we basically create the formula for linear regression. And this equation tells us that each unit increase in weight, the MPG decreases by approximately 5.34 units. And if you know the weight of a vehicle, you can directly plug it into this equation to estimate the vehicle's MPG. So then we have the residuals, which indicate the difference between the observed and predicted MPG values, as I mentioned. Here the minimum is minus 4.5432, which is the smallest residual, meaning one prediction is around 4.54 units above the actual MPG, because here we subtract predicted from observed, and if we get a negative value, it means that the predicted is above this value, above the observed value by this much units. And then we have the first quartile, which is minus 2.36, meaning that 25% of the residuals fall below minus 2.36. So 25% of the predictions are actually larger than the actual observed value by 2.36 units. Median is minus 0.12, meaning half of the residuals are below minus 0.125. So they are similar, but they are still a little bit above. So we can say that half of data are above this value. Like for half of data, predicted values are above the observed values. And then third quartile is 1.40, meaning 75% of residuals fall below 1.41. So this time observed values are larger than the predicted values by 1.41 for 75% of data. And then the maximum is 6.87, which is the largest residual, meaning one prediction is 0.87 units below the actual MPG. And the residuals should ideally be symmetrically distributed around 0, suggesting a well-fitted model without bias. And we can easily create a residual plot to check this visually. And we need to check one more thing. If the residuals are randomly scattered around the horizontal line at 0 with no obvious pattern, this supports the appropriateness of the linear model. It indicates that the relationship between MPG and weight is likely linear. But if you see a distinct pattern such as a curve, funnel shape, or clusters, it suggests that linear model might not be capturing all aspects of the relationship. So a non-linear model would be better in this case. So let's see. Here we say plot model $, fitted dot values, get the residuals, we give the title saying residuals versus fitted values. For X label, we give fitted values. For Y label, we give residuals. PCH is 19. Color is, what should we give? Let's see. Do we have more? Yes, we have it. Great. And then another thing we do here is we add a, we add it here. To add a line, we call the add line function. Then we say add a horizontal line at point 0. Make the line, what should we make it? Red. but that one, I think dark green is, or just blue, yeah, in this case. LTY is equal to 2. Now let's plot this. We can also change the line type from LTY. We can make it solid with 1, like this. So whichever you want, I'll make it dashed right now. By the way, if you want it to be more like, how to say it, like chic or not so plain, you can always play with this. There are some really good symbols that, oh, sorry, we have 26 in total, so this is the last one I can give. You can see what's the zeros, squares, 1, 7. So you can try all of these. Let's go with 19 because we like filled dots. Okay, so this was plot character. So what we see here is that they are kind of randomly scattered. We can see a distinct pattern. So there is like the linear relationship, which we'll see here. And another thing to say, it's not perfect, it's not symmetrical. We can also say that. Now let's continue interpreting. So we have the coefficient section, which includes the estimates for the intercept and slope with standard errors, t-values and p-values. The intercept is 37.28, meaning when the weight is 0, the model would predict an MPG of 37.28. Though this is not meaningful in this case because the weight can never be 0, this is still calculated mathematically. And then the coefficient for weight is minus 5.34, which we've already talked about, means that with each additional increase in weight, the MPG decreases by 5.34 when we hold other independent variables constant, but we don't have another one here in this case. And then the p-value of the intercept tests whether the intercept is significantly different from 0, so the predicted value of MPG when weight is 0. Is it significantly different from 0? While the intercept is usually less important for interpreting relationships in the data, its p-value can indicate if the baseline level is non-zero, which in this case it's significantly different because it's 37, it's not 0. And then the p-value for weight is what we need to consider because it tests whether the slope of weight is significantly different from 0. Since weight is our predictor variable, this p-value is crucial. Again, it tells us whether there's a statistically significant relationship between weight and MPG, and the low value strongly suggests that there is. Weight is a significant predictor of MPG. Then we have the residual standard error, which is kind of confusing at first. Look like what's 3.046 on 30 degrees of freedom mean. So it means that this value, so the typical deviation of MPG values from the regression line is about 3.05 units. That's all what we need to know. And degrees of freedom is 30, which we know as number of samples minus 1. And then we have the R-squared and multiple R-squared. These are also very important after the p-value because these indicate how if this is a good fit, this linear line. So here we have 75. So it's good, it's a moderately good fit, not very good fit because we need a like 90 or above 90 R-squared value for a very good fit. And then the adjust R-squared is slightly lower than R-squared because it adjusts for the number of predictors in the model. We'll see this more in multiple linear regression where we will have multiple predictors. So R-squared is generally defined as how much of the variation in MPG, so the predictor variable can be explained by differences in their weight alone, so the independent variable. So if we imagine plotting all cars' MPG values on a graph, there would be a lot of spread or variance in these values because MPG varies from car to car. The R-squared value of 0.7528 suggests that most of this spread, about 3/4, is predictable by knowing the car's weight. In other words, weight provides substantial insight into why some cars have higher or lower MPG values. For contrast, if the R-squared value had been much lower, like 0.2, then that would mean only 20% of the variation in MPG could be explained by weight. So we would need another factors in this case, like engine type, tire type, engine size, driving conditions, etc. And the remaining variation, which is 24.72, is due to other factors. So not all MPG differences are accounted for by the weight, which is expected because real-world scenarios usually involve multiple influencing factors. And how we calculate the R square is we divide the SS residuals, so sum of squared residuals, so differences between observed and predicted values, by the SS total, which is the total sum of squares, so differences between observed values and the mean of the dependent variable. Okay, now let's continue. And lastly, we have the F statistic. It answers the question, does this model with the given predictors explain enough of the variance in the outcome variable to be considered meaningful? So F statistic in regression analysis tests whether the overall model is statistically significant, meaning it checks if the independent variables taken as a group explain a significant portion of the variance in the dependent variable. So in our model, the F statistic tests whether the single predictor weight provides useful information for predicting miles per gallon MPG. So it compares two things. First, the amount of variation explained by the model with predictors, so the explained variance, and the unexplained variance, so the amount of variation left unexplained by the model, so the residuals, is called the unexplained variance, so the variance that isn't accounted by the predictors basically. And here is the calculation. We have degrees of freedom for the model, so the number of predictors, and the degrees of freedom for the residuals. The model degrees of freedom is determined by the number of predictors in our model. So for our case, it's since we have one weight, we have 1 degrees of freedom, 1 predictor, and then the residual degrees of freedom is calculated as the difference between N and P. So number of observations available for estimating the variability of the residuals after accounting for the predictors. So since we have 30 observations and 2 predictors, 2 parameters to estimate, so the intercept and the slope for the weight, the residual degrees of freedom would be 32 minus 2, so equals 30. And the F statistic is 91.38 with a very low p-value. So this high F statistic indicates that the model with weight as a predictor explains significantly more variation in MPG than a model without it. And the low p-value associated with the F statistic shows that this result is not due to chance. It's highly unlikely that the predictive power of weight on MPG is random. So the F statistic confirms that weight is a meaningful predictor of MPG. And we can also plot this. Let's do that. GG plot, we have our data as X is of course weight, Y is dependent variable MPG. We put each data point, we put our linear regression line, we give it a color which, let's say brown, okay, and then as title let's give linear regression PG versus weight. X-axis title is weight, y-axis title is miles per gallon, so called MPG, and team gray. Let's see. Oh, what did I do now? Title. And now we can see it gray. So brown is our linear regression line. We have our data points, and we can see that the data points fall closely to the linear regression line, showing a good fit. So the R squared and F statistic values are confirmed here, again emphasized. And then we will talk about the multiple linear regression now. So multiple linear regression is an extension of linear regression that uses multiple independent variables to predict a dependent variable. So we just increase the number of independent variables from simple linear regression to get to the multiple linear regression, and their formulas are very similar. The only difference is we have more x variables now, more independent variables in this case. So now let's try it. Now let's predict the car MPG with more variables. Okay. Can directly turn this into a data set like this. LMPG. And then we again have weight, but this time we also have horsepower. Right, okay. And then data is empty cars. Then let's get a summary. So first you can see the code section, which shows the linear regression model that has been fitted with MPG as a dependent variable and weight and horsepower as independent variables. And if when you want to add new variables, you just add them with plus like this, and then it works. If you want to add all the variables, you just put that here, then it adds all of them. See? Yeah. Look, now we have capture, AMBS, and all these kind of things. To make it simpler, I'll just add these two. And if you wanna add one last thing that I wanted to say, if you wanna add most of them but exclude some, like for example this one, you just say minus in front of it and it excludes it from all the independent variables. So now we can see it, as you can see here. Okay, now we can finally move on to interpretation. So in the residuals section, we have as minimum value minus 3.941. So there is a point where the predicted value is above the observed value by 3.941 units. And then we have the first quartile saying that 25% of the residuals are less than minus 1.6, representing the largest negative residual. And then we have the median that says half of the residuals are less than minus 0.182. And the third quartile says that the residuals are less than 75% of the residuals are less than 1.050. Now we can say that 75% of the data points are usual, like most of the data points till 50% are above the are where the predicted values are above the observed values. After 50% to 75%, there are some that have the case where the observed value is greater than the predicted. That's why we have a positive result. And then the maximum value says that there's a data point where the observed value is 5.854 more than the predicted value, which is the largest positive residual. Then we have the coefficients. So here each coefficient represents the estimated change in the dependent variable for a 1 unit increase in the predictor variable, holding other variables constant. So here for VT we have minus 3.87, which means that with 1 unit increase in weight, the MPG will drop by minus 3.87 approximately. And then for horsepower, with each increase in horsepower, the MPG will drop by 0.03, but it's not as drastic as a change as when we have just weight. So weight is a more important predictor of MPG in this case. And then the intercept is 37.20, which means if we put both weight and HP to 0, the model would predict the MPG to be 37.20, which is not realistic in this case. And then we also have the standard error that measures the average amount that estimated coefficient like the coefficient for weight or horsepower would vary if we repeated the regression with different samples from the same population. Since we are using all the samples in this case, we don't have to worry about that. But if we have a huge population like a city and we are sampling 100 people, then this standard error would give us a like estimation of how our results could deviate when we take different samples for each predictor. Since the standard error for weight is 0.63, it means that the estimate of minus 3.87 could vary by 0.63 mpg if we were to take different samples. The t-value is the ratio of the estimate to its standard error, and it's used to test the null hypothesis that the coefficient is 0. So for example, for weight, our estimate is 3.87, and then standard error is 0.63. If we divide them, we approximately will get minus 6.13, and that's how we identify the t-value. And then the t-value being minus 6.13 means that the coefficient for weight is about 6.13, standard error is below 0, which indicates a strong negative relationship between weight and mpg. Lastly, we have the p-values. The intercept is highly significant, as we can see here. And then the coefficient for weight is also highly significant. And the coefficient for horsepower is also significant, but not as much as weight and the intercept. The residual standard error is again the estimate of the standard deviation of the residuals. So it suggests that the typical difference between the observed and predicted values is about 2.593 in this case. The degrees of freedom 29 come from number of observations 32 minus number of estimated parameters 3 including the intercept. And then we have the multiple R squared that indicates that approximately 82.68% of the variance in mpg is explained by the model combining weight and horsepower. It was 75 before, as you might remember here. So with more variables, we can usually estimate more of the variance. I wanna actually see quickly how it would change if we used all the... It actually decreased. If you put a lot of variables, that would be of no use, but make the model estimate in a more difficult way, because it's so confused with all these variables, then it's not good. And if you have a lot of variables, especially with not much of a data, you need to usually reduce the dimensionality, which we'll learn with principal component analysis or other methods. Now let me HP, okay. After that, we can see that the adjust R squared is less, about 0.8148, because we had one more significant independent variable, but still a high value. The adjusted lessens when we had more and more variables. So F statistic is 69.21, which represents the overall significance of the model. A high value here indicates that the model provides a better fit than a model with no predictors, and since it's above 50, we can say that. And then the p-value is very little, less than 0.05 obviously, so which means that at least one of the predictors is significantly related to mpg. In this case, both of them are significantly related, as we can see it here. I forgot to show it to you, but you can also discard some variables if they are not related. Look, in this case, just weight is related. But it depends on which variables you combine, because look, horsepower and weight aren't much related in this case. But if you put them by themselves, then they are highly related. Now let's plot this. There are different ways you can plot it, but I'll plot it like this. T-cars. Since we have multiple variables, like just two independent variables, I'll color it as horsepower, because I want to show both of these. But if we had a lot of variables, then the data would be really highly dimensional and it would be really hard to see the dimensions. We would need to look at a high dimensional space basically. We did our scatter plot, now our regression line. Oops. We have the method lm, and then our formula is y x. We have to say that because in this case we can only show one of these variables in a plot, so we say that the linear regression line will be fit between weight and MPG, and HP will just be shown as the colors. Can the standard error, let's not show that. Color, is there baby pink or baby blue? No. Is there like navy? Okay, we have navy, that's good. And then labels, we have the title, which is multiple linear regression on empty cars. Our X label will be weight, and our Y label will be miles per gallon. And the color will be horsepower. Don't have to say these, but you can make them more specific if you want. And then team, can we get about this? Here you can see it. It's not really good to plot it like that because horsepower isn't a categorical variable. It's also continuous. But the only way I could think of showing you all of these is this way, because like the linear fit would be similar if we had also included the horsepower, but it would be, I think, more steeper because of these outliers. It would have gone like that to fit through them too. Other than that, it would stay approximately the same with being more steeper. This was our MPG versus weight. You can see it's the same 30. And our intercept was approximately 37, right? 7.28. Here, what was that? 37.23. It's actually less in this case, but it's hard to see really. Because the data points are more clustered and they fit pretty well, it might not even adjust. It depends how the model acts. And I think this was all for the multiple linear regression. Now we can finally move on to the polynomial regression. Let me see if this is the last. Oh yes, this is the last one. That's good. Okay, so the polynomial regression is a form of regression analysis where the relationship between the independent variable x and the dependent variable y is modeled as an nth degree polynomial. So it's not linear anymore, it's nonlinear. This allows for a more flexible fit compared to simple linear regression, particularly useful for capturing nonlinear data. And here we can see it, we have some degrees, x squared, and then x to the power of 3, and it goes to the n. Other than that, it's pretty much similar. Now let's test this using R. I wanted to give a real life example here, so I thought of using BMI since it's using BMI for this, since in BMI weight is linearly dependent to BMI and height is quadratically because V square height basically, and take the inverse of it. because you know the BMI formula is weight over height square. So I want to plot this. I was trying out different plots to show it to you as better as I can. But we'll plot it together now. Let's see. So firstly, what I've tried was I made both height and weight variable like continuous, which didn't give me a really good example. But if I keep one of them constant, then we definitely see their effect on BMI, their correlation with BMI. So I'll do that now. Gplot to z.c 73, then and 100 height. Now let's keep this constant, say 150. You can give anything you want. Weight will be variable in this case. Let's give the mean as 60, standard deviation 15. BMI is weight by height squared. And then our data is the dot frame, height, weight, and BMI. Now if we look at our data, we see height is constant, and according to that BMI changes. Now polynomial BMI model, say linear regression BMI. So we say poly weight 2. What this does is that it creates a formula with an intercept, and then it will write b1 beta 1 multiplied with weight, just weight. So it will look at the linear linear effect of relationship between weight and BMI first of all, and then it will also take the second polynomial and look at the quadratic relationship between weight and BMI, and it will, in the coefficients, we will be able to see which one is more dominant, the linear or the quadratic relationship, or if they are statistically significant. And we can't forget our data. Now let's get the summary. Polynomial data. My camera is in the way again. We put it here. Okay. Sorry for that. Now we can see that's great. So here, since it's mathematically proven that it's a perfect relationship because we got the BMI with this formula, we might add some noise to make it more real life like. But this isn't a really good example, but I couldn't think of any other example to give. So let's think that we don't calculate the BMI like this. We actually gotten these values. Let's think of it that way, because it will help us make a better estimation, like better interpretation means zero is like some noise, a little BMI data with noise. Oh, false. Now we can see that there are some noises here, especially in height also. So now we can see that the linear relationship is more profound here. I want to also plot this so that we can understand it better while also plotting. Let's see. And then let's give that a title, Polynomial Regression or BMI weight relationship. Maybe that's a better thing, because BMI and weight are linear, have a linear relationship. What about this? And then with height we will see a polynomial, so quadratic relationship after this. BMI, say team minimum, or maybe team dark is better because we have yellow dots. Okay. So I've opened RStudio again after closing it because it was kind of stopping a lot and it was really slow. So here we can see an almost perfect linear relationship which we've expected. And if you look at the results, we can use line width. Let's see. It's always important to look at these warnings. Line width. One is better, I think. But we put size here. Okay, so we can see that it's almost perfectly linear, which is good. And in our values, we see that the linear relationship is statistically significant, while the quadratic one isn't. Intercept is also statistically significant, and our R squared is really high. Our F statistic, on the other hand, is really low, which is good. Other than that, did I want to say anything? Let's see. We explain a significant portion of the BMI with weight, and then we have our residuals again, but you know how to interpret these R called. So that was all actually. Let me now do the same thing for height, because this was an example for a linear one. Was it here? Yes. This was for height. Now I've taken the height as variable and the weight as constant. Let's say BMI versus now height. There's height. Okay. Now you can see a quadratic relationship finally, because BMI is the inverse of the square root of height. So when we increase height, the BMI decreases basically, but in a curved pattern, because we take the square and then divide it by 1, take the inverse of it. And here you can see that still the linear relationship is significant. Also we have the curved relationship, polynomial relationship, that's significant. Other than that, the multiple R squared result is really high. And F statistic is also high. Let's see how much what I can interpret more. So again, the linear relationship basically proves that they are negatively correlated. So there is a negative relationship between them, and this high value 47 shows significant curvature. And then let's see, R squared also says that the BMI variation is explained by height. Here the very high F statistic with tiny p-value confirms strong relationship. I'm thinking if I missed anything. And the residual standard error lastly means typical prediction error is about 1.576 BMI units. It can deviate from it above or under. And then I think that's all with this. The last thing I want to say was the polynomial regression. So we are done with our video today. Congratulations if you persevered throughout all these conclusions. I hope you could understand it clearly. Thank you so much for listening and have a great day. See you in our next video where I talk about more regression. Bye.